Welcome back. We've now talked about solubility. We've talked about solubility in mixtures and things like the common ion effect, how pH affects solubility. And in all of these things, right, we said that some things are more soluble than others. Some things will actually precipitate out. Right? What is precipitation? It's when a solid forms, when you mix a couple things that are liquids, there's no solid, and a solid forms. Now, why would something precipitate? Well, if we just write a generic reaction, AB solid goes to A plus aqueous plus B minus aqueous, what does it mean to precipitate? It means that this is formed, right? That the solid is formed. What does that mean? That means this reaction is going to the left. When do reactions go to the left? Reactions go to the left when Q is greater than KSP. Why SP, right? Because we have a solid forming its constituent ions as our equilibrium reaction. That's just a KSP. Remember, KSP is just a K. We say SP, we know, oh, we're talking a solid breaking apart into its ions. So right when Q is greater than K for this reaction is when a solid is going to form. So we can actually use that to our advantage and determine, hey, are solids going to form when we've got certain mixtures of chemicals together? So we're going to do an example that looks something like that right now. So we're going to make a solution, and it's going to be 300 milliliters of 3.5 times 10 to the minus third molar nickel 2 nitrate. And it's going to also be mixed with 250 milliliters of 1.5 times 10 to the minus third molar sodium carbonate. And we're going to try to figure out what, if anything, is going to precipitate. Okay, what will precipitate? If anything. How are we going to do that? Well, we've got to check whether Q is greater than KSP, but Q is greater than KSP for what? Well, we have to think about what's present in solution and what can possibly be made in order to know what Q's and KSP's to look at. So let's pretend and let's draw this out. For a lot of people, having the visual drawing of this is really, really, really useful. So nickel 2 nitrate, what's the formula of that? It's going to be NiNO3 2. But what do we know about all nitrate compounds? They're always soluble in water. What does it mean to be soluble in water? It means it breaks apart into its constituent ions, and you actually get nickel 2 plus and 2 nitrate ions. So we know in our solution we're going to have some nickel 2 plus and we're going to have some nitrate ions. I'm not worried about the stoichiometry in my beaker there, but there is stoichiometry of 2 nitrates for every nickel. Sodium carbonate, Na2CO3. How did I know that? Because I know by memorizing that carbonate is CO3. It's got a -2 charge. Sodium, I know, it has a +1 charge. Balance 2 +1 charges for my -1 charge. And that's going to break apart into 2 sodium ions and a carbonate ion. So what do we also have? We also have sodium ions and we have carbonate ions. And so what we're going to try to figure out is what can possibly precipitate in this particular case. Well, we can eliminate things, because if you remember, all sodium salts are soluble and all nitrate salts are soluble. So I don't have to care about whatever they might or might not combine with to determine whether something's going to precipitate. I don't have to worry about whether sodium is going to combine with carbonate or sodium is going to combine with nitrate, because they're not going to, because even if they did, they'd be soluble. If my only reaction is worrying about precipitation, the forming of a solid, then I don't need to worry about that. But I do need to worry about whether nickel and carbonate might form a precipitate. So let's write that reaction. Now, I'm going to write it as a reaction of the solid forming the ions, even though the reaction I'm worried about is the ions forming the solid. Why? Because I can look up K values for a solid forming ions. I can't look up K values for ions forming solid. So I've got that, goes to nickel 2 plus aqueous and carbonate aqueous. So there we go. I've got my K reaction, my KSP, and I can just go ahead and find the KSP value for that. So I look it up in a table, and I find that the KSP is 1.4 times 10 to the minus 7th. And so what I have to calculate is I have to calculate my Q and see if Q is greater than KSP. What's Q going to be? Well, remember, Q has the same form as K. It just means that the current conditions as opposed to only at equilibrium conditions. So there's my Q. I've got to find my nickel concentration and my carbonate concentration, which means I got to go scroll back up here a little bit and think about these two different solutions that I was given. 300 milliliters combined with 250 milliliters into the same beaker. What's my total volume going to be? My total volume is going to be 550 milliliters. Right, when I combine those, 550 milliliters. So when I've got that 550 milliliters total volume, it means I diluted both of those solutions, right? You see the theme here? A lot of dilution problems. Okay, so we're diluting both of these things. So let's go ahead and figure out my diluted concentration. My diluted concentration of nickel, but we weren't given nickel, we were given nickel 2 nitrate. But remember, nickel 2 nitrate forms stoichiometrically 1 nickel. And so 3.5 times 10 to the minus 3rd molar nickel 2 nitrate is the same thing as 3.5 times 10 to the minus 3rd molar nickel, because it forms that in a 1-to-1 stoichiometric ratio. So we're going to do M1V1 equals M2V2. And so I've got my 3.5 times 10 to the minus 3rd, oops, I put 2 minuses there, 10 to the minus 3rd molar times my initial volume of that is 300 milliliters. And then I'm going to divide by my final volume of that, which is 550 milliliters. And if I do that, I get 1.9 times 10 to the minus 3rd molar. I can do my same thing for my carbonate concentration. And that's going to be 1.5 times 10 to the minus 3rd molar times 250 milliliters divided by 550 milliliters. And I get 6.8 times 10 to the minus 4th molar. Then my Q is just going to be multiplying those. 1.9 times 10 to the minus 3rd times 6.8 times 10 to the minus 4th. Professor Clements, you forgot your units. Remember, once we get it into Q, once we get it into K, we've divided by a reference unit of 1 molar, so our molars go away. Technically, it's the activity, but we're not going to worry about that in this class. You multiply that out on your calculator, you get 1.3 times 10 to the minus 6. Remember, K was 1.4 times 10 to the minus 7th. Since Q is greater than K, the reaction goes left, which means we precipitate our nickel 2 carbonate. So that's how we can actually determine whether a mixture of solutions or even a given solution will undergo precipitation, is by calculating the Q for any possible precipitation reaction. If I had multiple precipitation reactions, I could calculate multiple Qs. That's okay. That's perfectly fine. Now, it turns out there's some detail to that we won't really get into, but you can do that kind of stuff. So reaction goes left, I precipitate. If, for example, my Q had ended up to be 1 times 10 to the minus 9, then my Q would have been smaller than K, and it would say that even though we mix these two chemicals that are technically insoluble, I have low enough concentrations that there is no precipitation that takes place. I don't form any nickel carbonate because my equilibrium is still shifted to the right, not to the left. So there we go. So we're actually going to form out some nickel 2 carbonate precipitate. We're not going to calculate how much. We could, because how much would you get is actually until you get down to Q equals KSP, and so you can do those calculations. We're not going to do anything like that in this class. We just want to know, does it precipitate? In this case, it does. So your turn. What chemicals, if any, precipitate when 250 milliliters of a 4.3 times 10 to the minus 3rd molar solution of lead 2 nitrate is mixed with 150 milliliters of 0.024 molar solution of magnesium bromide? You must justify your answer with math for any credit. Of of course, credit online when you're, anyway. Just in case you need it, since I didn't want to have you looking things up while you're trying to do this stuff, just in case you might need it. The KSP for lead 2 bromide is 4.67 times 10 to the minus 6. All right, go. Since I gave you a pretty strong hint, right, you kind of know where you're going with this one, but let's go ahead and write it and draw it out anyway. We've got lead 2 nitrate. We know that's going to dissolve into lead 2 plus and nitrate. And we've got magnesium and bromide. Right? And again, there's some stoichiometry there that we're not paying attention to. It's MgBr2, it's PbNO3, parentheses 2. So we've got that there. But what we really want to know is this picture is what ions do we have and what ones do we not need to worry about. We don't need to worry about nitrate. Nitrates are always soluble. So we need to worry about the possibility of lead bromide or magnesium bromide. Now, what do we know about bromide? Generally soluble, except for lead is one of the options. So magnesium and bromide we don't have to worry about because it's on the list of soluble things, if you remember. But given the hint that you had, we have to worry about lead bromide. So Br2 solid goes to Pb2 plus aqueous plus 2Br minus aqueous. And again, how do we know it's Br minus? Because that's what bromine forms when it forms ions in solution. It doesn't form Br2 with a minus, it forms Br minus. And so to get the stoichiometric portions right, we have to have 2 of those. How did I know that? It's from experience. You see this over and over again. The halogens, they generally form just single ones with a minus charge. And so you see that enough times and you start getting used to that. So that's one of the things you're developing over time is how to get used to that, how to see these things and be like, oh, I've seen this before. We look up a KSP for that one. It's 4.67 times 10 to the minus 6. So we're going to compare our concentrations. I'm not going to show you every single step here. Right, what do? We add up these guys, 250 plus 150 is 400 milliliters total. We do an M1V1 equals M2V2, and we find out that the concentration of Pb2 plus is 2.67 times 10 to the minus 3rd molar, and the concentration of Br minus is 0.030 after dilution. You're like, how could it be 0.030 after dilution when it only started off as 0.024? That doesn't make any sense, Professor Clements. Well, no, it started off as 0.024 magnesium bromide, right? MgBr2. Which means there's twice as much bromide in there, so it's actually 0.048 molar bromide. And when you dilute that, you get 0.030. Okay, so there's a lot of little subtleties in here that you need to keep track of. Right? MgBr2 has 2 bromines, so I got to do the stoichiometry on that one. So bromide, 0.030 molar. When you multiply those 2 out, you're going to find Q equals Pb2 plus. And what do you have to do, right? Since you've got 2Br there, this is going to be Br minus squared. And so 2.67 times 10 to the minus 3rd, 0.030 squared. And that is going to be equal to 2.4 times 10 to the minus 6. We look back up, we're comparing to 4.67 times 10 to the minus 6 equals KSP. What are we? We are less than KSP. Q is less than KSP, which means nothing. Which means nothing happens. Q is less than KSP. The reaction actually wants to continue going to the right. It wants to dissolve more stuff, but we're not there. We don't have more stuff to dissolve. We just have this aqueous stuff, and so no precipitation is going to happen. E. Not the answer you're expecting. You were expecting to get a precipitate, but hopefully when you did the math out, you're like, well, nothing precipitates, and that's what we get. If you didn't square this one, guess what? You would have gotten that the lead precipitates. I put that in there on purpose. I put it right on the edge. So if you squared it, you got the right answer. If you didn't square it, you got the wrong answer. Not nice of me, is it? Okay, but that square is important. You got to have that square in there, that coefficient, that power is important to have in your K expressions. All right, how are we going to use that? How are we going to use that? Let's say we had a beaker here, and it contains some lead ions, and it contains some copper ions. Now, actually, sorry, copper 1+. Now, disposing of copper ions, you can do it if you had waste. Disposing of lead ions, pretty expensive, right? Because lead's pretty nasty stuff. So how could we separate these things, right? They're mixed. Is there a way that we could separate out the copper from the lead so that we don't have what's called mixed waste? Because mixed waste is even worse. How could we possibly do that? Well, it turns out you can use the relative solubilities of these things to figure out how to separate them. So if I look up the solubility of lead 2 iodide, our KSP is 1.4 times 10 to the minus 8th. And if I look up the solubility of copper 1 iodide, my KSP here is 5.3 times 10 to the minus 12th. And so you can see copper iodide is significantly less soluble than lead 2 iodide is. And you're like, no, professor, you told us you can't just compare KSPs when they fall apart differently. No, you can't. Okay. However, if you do the math, you'll find out that copper iodide is significantly less soluble. So you actually have to do the x squared and all these 2x squareds, 4s divided by things. Yes, you have to do that. But you'll find that the copper iodide is significantly less soluble than the lead 2 iodide. So if I start to add iodide in here, obviously when I add a tiny, tiny bit, nothing happens. But as I add a little bit more, what's going to happen first? The copper is going to start making my solid copper iodide. And it turns out I can add quite a lot of iodide before any lead is going to try to come out of solution. And so I actually can keep adding iodide until almost all of the copper has been taken out of that solution. And now I just have a solution of lead. So let's do an example. Let's have a solution where we had 1.0 times 10 to the minus 4th molar copper, and we had 2.0 times 10 to the minus 3rd molar lead 2+. We want to know what is the maximum amount of iodide concentration before the lead 2 iodide precipitates. Right, so we can add up to that, and we'll notice that the copper iodide precipitates. And we're going to answer a question that wasn't asked here along the way. Let's figure out when the copper iodide first starts to precipitate. So for copper iodide, my KSP is going to be the concentration of copper times the concentration of iodide. Well, I already have the concentration of copper. It was given to me. It's 1.0 times 10 to the minus 4th concentration of iodide there. But I actually also know KSP because that was given to me as well, and that was 1.4 times, oops, sorry, for the copper iodide, 5.3 times 10 to the minus 12th. Well, look at that. I've got an equation with one unknown, so I can actually just solve that for I minus by dividing both sides by 1 times 10 to the minus 4th, and I get 5.3 times 10 to the minus 8th molar. So it turns out when I get to a concentration of 5.3 times 10 to the minus 8th molar, that's the moment when copper iodide will start to precipitate. So if I'm at 5.2 times 10 to the minus 8th molar, no precipitation happens. If I'm at 5.4 times 10 to the minus 8th molar, something is already precipitated. 5.3 times 10 to the minus 8th, when I'm right on that line, nothing's precipitated yet, but as soon as I add a tiny bit more, stuff will start precipitating. So what I want to know next is how much iodide can I add before the lead starts to precipitate? And so for my lead 2 iodide, my KSP was 1.4 times 10 to the minus 8th. And that's going to be lead and iodide squared. Why? Because it falls apart into Pb2 plus and 2I minus. So we get the I squared. And we plug in our values there. We get the 1.4 KSP times 10 to the minus 8th is equal to our lead concentration. That was given to us as 2.0 times 10 to the minus 3rd molar. And then I minus squared. So I divide both sides by 2 times 10 to the minus 3rd. I take a square root, and I get that I minus is equal to 2.6 times 10 to the minus 3rd molar. Okay. And that is when my lead starts to precipitate. So that's actually a pretty wide range, right? I can have iodide concentrations from 5.3 times 10 to the minus 8th molar all the way up to 2.6 times 10 to the minus 3rd molar, right? 5 orders of magnitude. I got a lot of leeway before any of the lead iodide starts to precipitate out. And what's even cooler is that as my copper iodide precipitates out, it's taking iodide out of the solution. And so I can keep adding iodide, and I'm not actually upping the concentration by all that much. So it turns out I can take almost all of the copper iodide out. We're not going to calculate that precisely. We could, but we're not going to calculate that. But just knowing that these are the ranges, that from a concentration of 5.3 times 10 to the minus 8th to 2.6 times 10 to the minus 3rd, I'm going to be precipitating copper 1 iodide, but I'm not going to be precipitating lead 2 iodide. And so I can use that to separate out ions in solution. Neat stuff, I tell you, neat stuff. So another way that people use the relative solubility of things is something called qualitative analysis. Now, we're not going to get a chance to do that this semester, but you already did something somewhat similar to it in Chem 50. Right? You did spot plates where you're putting in little chemicals and things like that and testing for the presence of silver, lead, and mercury. And you did that by adding hydrochloric acid, because we know that the chlorides are insoluble with lead, mercury, and silver. And so if you add those and they precipitate out, you know you have one of those ions. And so that's a way of qualitatively, right? Because all you had to do is drop and look for a precipitate, qualitatively figure out whether you have moderate concentrations of those ones. But the fun part is you can then use hydrogen sulfide, H2S, to test for the solubility of a bunch of other things, which is mercury, cadmium, bismuth, copper, tin, arsenic, lead, antimony, because they have vastly different KSP values from 10 to the minus 3rd down to the 10 to the minus 54th. I mean, what is that, 40 orders of magnitude? Rarely in life do you ever get anything that varies over 40 orders of magnitude. That's a crazy amount. I mean, that means I have $1 in my bank, and then I've got more money than has ever existed in the history of man and exists now in the bank, right? And actually, 20 orders of magnitude more than that, or more than that. It's just crazy numbers, okay? And so what you do, you've already added a bunch of concentrated HCl. So when you add hydrogen sulfide, Le Chatelier's principle says, since I've got a lot of free hydrogen ions in there, my H2S is going to primarily exist as H2S, because I've got so much of this in there that this equilibrium is going to shift all the way over. So what you do is you start so your concentration of HS and your concentration of S minus, which is S2 minus, which is what these things actually precipitate with, is extraordinarily small. So what you do is you start titrating with hydroxide ion. And as you start titrating with hydroxide ion, you start removing some of that, and you start to shift this equilibrium to the right. And in fact, you can even start shifting that next equilibrium to the right to form some amount, very small amount of S2 minus. But, if you've got a KSP of 10 to the minus 54th, boy, it doesn't take much of that S2 minus before things start to precipitate. So if you're monitoring your concentrations, which is your volumes if you're doing a titration with hydroxide, very, very carefully, you can know, oh, look, when I got to exactly this value, this precipitate, a precipitate, you don't know what it is, but started to come out. And you can calculate, oh, that was this concentration of S minus, which means it must have been this particular metal because that's the only one that has a KSP and that would precipitate in that range. And then you keep precipitating things out. As you titrate with hydroxide, you're going to form more and more S2 minus, and you just go down that list of precipitating all these different things at different concentrations. So it's a really neat way of separating out different metals that might be in a system. Now, of course, there's other ways of doing that nowadays. You can take a solution that's got a bunch of different metals in it, you can put it into what's called an atomic absorption spectrometer, and it's kind of like CSI. It'll just spit out a printout of, well, here's what was in your solution, here's their relative concentrations, have a nice day. So that is much easier, and that's what most people do nowadays who have access to that type of equipment. But there's some really cool chemistry that goes on in some of this old qualitative analysis. So once you start to do that enough, you now get to the point where you've got a neutral solution, you've neutralized all of your acid, and you start to get a basic solution. And then in a basic solution, your iron, your chromiums, and your aluminums actually start to precipitate out because they form hydroxides. Then you can test for alkaline earth metals by adding phosphates, because those will precipitate out with phosphates. And then for the alkali metals, those are a little harder. You have to use flame tests. And that's pretty much the only way to test for them easily. And that's actually what an atomic absorption spectrometer does, is it does flame tests, it burns things, and then looks for the signatures of them. So that is what it does, but it can do it for pretty much all the metals. So neat thing, qualitative analysis. We're not going to do much with that this semester, but I just wanted you to see it so you can understand that there's some really neat chemistry that we can do with solubility. The last topic for this video is amphoteric hydroxides. What is an amphoteric hydroxide? Well, if you remember, water was the first thing we talked about as being amphoteric. And what did it mean? It means it can act as an acid or it can act as a base. And it turns out there's some hydroxides out there that can do the same thing. And you're like, well, no. A hydroxide, it's got hydroxide on it. It's going to give away hydroxide. It's going to act as a base. But that's not always true. Let's look at AlOH3, aluminum hydroxide. It turns out if you add water to that, if you add acid to that, it's going to dissolve it, Al3 plus 6H2O. And so what do you have, right? You've got an acid, and this guy acting as a base. The H3O is giving away its H+, the aluminum hydroxide is accepting it, and it's forming a aqueous solution. An aluminum hydroxide is a solid, so you're adding acid to a solid, and you're going to dissolve it. But that's great. Well, what happens on the other hand? How is this amphoteric? Well, that must mean there's a way of adding base and having it react. And what that reaction is you make an aluminum hydroxide, ion complex, which we're going to be talking about in the next video, a complex ion formation. And this one is also aqueous, right? So you're taking that one, hydroxide, boy, that's got to be a base because that's our favorite base in the world, which means this guy's acting like an acid in this case and forming this one. What's really neat is you have this solid that is definitely pH dependent on how it reacts. But no matter whether you add an acid or a base, it'll dissolve. It just dissolves into different things. So if you add a base, it acts like an acid and dissolves into this ion complex. If you add an acid, it'll act like a base, and it'll dissolve into just the free aluminum ion. So some neat chemistry there in amphoteric hydroxides. What's even really cooler, right? Theoretically, if you start with aluminum 3+ and you start adding hydroxide, eventually what you should make is this guy. But then if you keep adding hydroxide, you should make this guy. So what you could actually do is titrate with hydroxide, start with an aqueous solution, get a solid precipitating out, the aluminum hydroxide, and then keep going, and you'd actually get the ion complex at the end, which is kind of some neat chemistry. All right, thanks so much for listening. Have a wonderful day.